Okay, welcome everybody to the Confidential Computing, Protecting Applications and Data in Use webinar. Before we get started, let me address a few housekeeping items. First, we are going to be recording the webinar and you will automatically receive an email with a link to the recording. We will not be distributing presentation slides separately from the recording, but we do invite you to watch the recording. Throughout the presentation, if you have a question, please input it using the Q&A button that you see on the right, and you'll see a dialog box where you can submit questions and choose optionally to make that an anonymous question. So we encourage you to submit questions. We're going to be taking all questions at the end of the webinar. So please submit them. We may, depending on the question, answer them by text during the webinar or answer them verbally at the end if we think it's useful to everybody and to have some discussion on the topic. Let me start with some introductions. My name is Seth Knox. I'm the Outreach Committee Chair of the Confidential Computing Consortium, as well as the VP of Marketing at Fortanix. We also have an all-star cast of CCC members, including Nellie Porter, who's the lead product manager at Google. She's going to be talking about how customers are using confidential computing. Next, we'll have Dave Thaler, who's the Technical Advisory Council Chair of the Confidential Computing Consortium, as well as a software architect for Microsoft Research. And then we have Ava Black, who's the open source program manager for Microsoft Azure Confidential Computing, and will be taking us through different trends in adoption and open source projects related to confidential computing. Before we get into the meat of the presentation, let me do a little introduction to the Confidential Computing Consortium itself. We're a community that's focused on promoting the protection of data in use, as well as open source projects related to confidential computing. We were founded a little over a year ago at the Open Source Summit North America. We're a combination of vendors, academic institutions, open source projects, software developers that are all collaborating to protect data and applications in use to make sure we can reduce the threat of data breaches, insider threats across public cloud, edge, and on-premises data centers. I welcome you to come to our website, which is confidentialcomputing.io, to learn more. We'll have a few resources for you at the end to learn more. The Confidential Computing Consortium is made up of a number of members. You see the logos here. This spans cloud providers, academic institutions, developers of software that are focused on confidential computing, all the way down to chip and hardware manufacturers, which are essential to the concept of a hardware-based trusted execution environments. So our membership has grown over 60% in the first year, and you can see that we have some of the largest and most reputable members across those organizations, and it's also very international. So there's companies from Europe, Asia Pacific, as well as North America. So we welcome you to come and visit the website if you're interested in becoming a member or participating in one of the open source projects. With that, let me start off by introducing Nellie Porter. Nellie's going to take us through some of the customer use cases and how people are starting to use confidential computing, so that you can have a quick introduction to that. Nellie, would you like to get us started?
Thank you so much, Seth, for introducing me. Let me go and start this discussion about data protection challenges that our customers and users are raising their concerns. So one of the common, and I was trying to synthesize it in these 4 bullets, but one of the biggest concerns, I guess, in today's digital world is how our users and our customers protect sensitive data in their IP if they're developing software and want to ensure that nobody would be able to assembly again, get access to that. Our customers trying to keep the compliance and the protection and work with regulations whenever the data, whenever the code is actually happening to run. They want to ensure that the same happening when they run it on premises or in the cloud environments or in the hybrid environments as well. There is a new use case that's rising that was not been possible to make happen in previous environments. And I would say it's how customers and different companies collaborate with other companies without sharing their sensitive data. With, again, COVID investigation, as you can imagine, more and more research organizations coming together to contribute the very sensitive data sets and trying to ensure the results of their research will benefit all of them and all of us. And finally, how users and customers will protect the client's data, their own data. All of those concerns continue coming. And I think confidential computing is the solution for some of those concerns. Next slide, please. There is no magic bullet to protect customers and users completely. And the goal for us is to build a very, very high defense in-depth protection. And starting with limiting visibility and access to sensitive data. As you probably know, encryption is a common way to safeguard and protect sensitive data and limited visibility. There is well-known technique how our users, their devices, and customers, when they sharing the data with, for example, cloud, can ingest this data, keeping it encrypted. There is also very well-known technique and multiple mechanisms how someone would be able to keep data encrypted at rest. It means storing this data for their backups, etc. But all data has to be processed. It needs to be indexed, queried, it needs to be trained on or inferred on. And it means data needs to be processed, still continue to be encrypted when it's in use. There is no current solution or not previously exist current solutions that would be able to do that. So let's go to the next slide and explain what confidential computing can help customers to deal with. There's multiple more detailed use cases I want to go with you on. And it doesn't matter if it's public cloud or happening on personal devices and somewhere in between. There is necessity to protect secrets, being keys, credentials, tokens, and being able to protect it such ways that they cannot be leaked or used for any inappropriate situation. There is plenty of personal user data collected on personal devices that have to be protected and not exposed by any means, shape, and form, only for intended purposes. As I mentioned earlier, the collaboration use case when multiple parties have to communicate and get to the common results. It's very common use case from multiple companies when they need to collaborate and share the very sensitive data sets. There's plenty of use cases coming from financial markets and fintech companies, but also from end users when they're trying to process a payment, make the payment to ensure that their sensitive information, the private information, continue to be private. There are more and more interesting opportunities to utilize blockchain for the same needs to protect sensitive PII data as well. And as you can imagine, the world of IoT devices is blooming, all of them collecting and part of our personal lives and being able to process this information securely and with privacy preserving technique is very important for us. And there is edge ability for us to do and connect the devices, personal devices and IoT devices with a much more powerful cloud environment. And all of that is definitely have to respect privacy of the data that they accessing to. And confidential computing is a way how we propose and moving forward to accomplish this goal. Next slide, please. We believe in Confidential Computing Consortium that confidential computing is a critical industry effort that will move secure computing to the next level. We want to focus on use cases, not only on the tech that are top of the mind for our customers and users. And we also want to ensure that our ecosystem and our community are part of conversation, because together we would be able to solve this very complicated problem and keep the privacy and security of our users, our companies, and our clouds. Thank you so much. Next slide, please. And I will pass this conversation to Dave Salah. Dave?
Thank you, Nelly. So I'm going to be talking about the definitions and threat model. So I chair the Technical Advisory Council, which is more the technical body within the Confidential Computing Consortium. So next slide, please. One of the first things that we did was we had to define, when we use the term confidential computing, what do we collectively mean? I mean, that's the name of our consortium. So we needed to come up with a definition that was going to be the baseline that the consortium was going to use that all of our members could agree on. And this is what we came up with. Confidential computing is the term, is the protection of data in use by performing computation in a hardware-based trusted execution environment. Now, in about 2 slides, I'm going to come back to what's the definition of a trusted execution environment. But all of the words on this slide here were carefully chosen, and it's also important what's not in here. So next, please. In particular, the definition is chosen specifically to be independent of topological location. So Nelly talked about whether it's in the cloud or on a user's device or anywhere in between. Notice that the definition is independent of where the computing is being done. It's also independent of which processor does it. Is it part of some regular processor? Is it a separate processor? Again, the definition is independent. And lastly, it's independent of whether the technique used for protection is encryption, which is the most common technique, or whether there's something else. It's not part of the definition, even if it is part of the normal solution. Now, I also want to concentrate just on that one word, by, for a second here. But if you have further questions, there's a reference. Go ahead and click next. There's a longer discussion of how we came up with this definition and many other terms that we found across the industry, because we've done this survey of many other organizations and what terms they used, and other terms had various competing definitions. But here we had a term that was not having competing definitions already, so we had this opportunity to define it. And so the word by in here is important because this is not the only technique for protecting data in use. This is the protection of data in use by using a hardware-based TDE. Okay, next slide. So there's many other related terms. And as I mentioned, the problem in all the related terms is there's multiple competing definitions. Just about every term on the slide has multiple competing definitions. Hence that disclaimer there that those lines are really fuzzy. Just to take one example, the term privacy preserving computation has at least 3 definitions. Where one would equate it with the term multi-party computation, one would show it as being the combination where it's shown on the slide here, homomorphic encryption and multi-party computation, and another definition encompasses everything on the entire slide, meaning synonymous with protecting data in use. And so because of these all fuzzy lines and things, that's why we had to come up with what do we mean by confidential computing. And you can see for confidential computing, if we scope protecting of data in use down to the bottom left corner where we have hardware TEEs, that's the part where confidential computing covers, okay? But all of these other things are in this space, and I'll talk about a little bit about the relationship between confidential computing and other related techniques. Let's go ahead and go on, yeah, that's next slide, yeah. So I said I would come back to what exactly is a trusted execution environment, because again, there is multiple competing definitions that are out there. So we work together with some of the other standards organizations. So for example, the IETF, the Internet Engineering Task Force, and the CCC, we wanted to use the same definition of what a trusted execution environment is, given that, standards organizations like the IETF focus on specifications, whereas the Confidential Computing Consortium focuses on the open source aspects that Ava is going to talk about later. And so we wanted to have a common definition so that we would work well with these other organizations and be able to have a clear division of labor where we're working on the same problem and using the same terminology, where it's easy to correlate things between standards and white papers and vendor marketing materials and open source projects. We wanted a common set of definitions. And so here's the definition that we collectively agreed on of what we're using for the term trusted execution environment. So in particular, it's any environment that provides some level of security assurance of three main properties, right? The data being held inside that environment has to be kept confidential, meaning it can't be modified or leaked, it can't be leaked outside that environment. Data integrity, meaning it can't be modified or deleted or replaced by code running outside the TE environment. And then finally, that the code running that environment is the code that you think it is, right? The code itself can't be modified or new code injected, things like that. And so we call those data confidentiality, data integrity, and code integrity. So anything that meets those three criteria can be called a TEE. And of course, we're going to focus in the CCC on things that are hardware-based environments that meet these three. And there's various other properties that are not part of the definition that are also typical but not required in the definition of a TEE. So let's go to the next slide. So this slide shows a bunch of the criteria down the left, and you can see the boxes around those three that we consider to be core definitions. In other words, if something doesn't have a yes, 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 then we don't call it a TEE. We call it something else. Now, as you start looking at the cells here, and I'm not going to walk through all the cells, I'm going to talk about some of the columns and things, but it's important that all the cells in here is an example. So if you take an example hardware TEE, then it's going to have some particular values in there. An example homomorphic encryption algorithm would have a particular set of values in the cells. And a particular TPM model and a particular DPM vendor would have a particular set of values in the cells here, right? All of the things in the cells here are not necessarily true for all possible, say, algorithms or TPMs or whatever. It varies. And so this is an area where vendors compete in even different models, and the extent to which something is no or yes or somewhere in between, it varies by vendor, by model. It's an area of competition. It's an area of innovation and so on. But what's important is just to step back for a second and say, well, independent of any particular cell here, what are some broad generalizations that we can kind of make to help understand what the definitions of the terms are and what's more typical out there, even if there's atypical things there. And so you can see for hardware-based TEEs, it's yes, yes, yes inside the box because that's the definition of a TEE. For example, homomorphic encryption is algorithms by which you can encrypt things and then perform computations on encrypted data, such that the computation could be performed in a location in the topology that never has access to the unencrypted data. Okay, so that's one which certainly provides data confidentiality because it never gets any data that's not encrypted. But by itself, taken alone, it doesn't provide any guarantee that the code being run is the correct operation. So for example, if you have rows in a table, are you summing them or are you multiplying them, right? Homomorphic encryption by itself doesn't protect against attacks like I'm going to replace the summation operation with a multiplication operation. And so this gets to the point at the bottom of the slide, which says that all these things are not necessarily competing technologies, right? You think that the space that was covered in the concept, the Venn diagram of concepts before, there's multiple techniques in the space of protecting data in use. Right? They're not necessarily competitors. They can be used in complementary fashion. So for example, you can use a TEE on the edge to encrypt your data, then send it to someplace doing homomorphic encryption. That's one way to combine things. Another way to combine things is to say, well, that homomorphic encryption doesn't provide, the code integrity piece. And so that's the one weakness. But if you did homomorphic encryption inside of a TEE, then you can. And so there are ways to combine these techniques to get even stronger security. For TPMs, for example, typically TPMs will take care of cryptographic operations and protect the keys. But if you wanted to do, say, an encryption operation, it would encrypt whatever data you send to it from the main CPU, right? The TPM does not sort of verify that the data being sent to it to encrypt is the correct data. You have to pair it with some other technique to do that. Okay? And then you see the other properties down the left side, which I'm not going to go through the cells, but it's worth saying something about the different properties, right? So code confidentiality, right? The ability to say, I have some intellectual property, for example, in the code, or I have some secrets in the code, and I want to put that code in some place. So maybe you sell a device that's an IoT device or a gateway or something like that. You have some intellectual property there that you don't want somebody else who buys the device to be able to crack that out and understand what it's doing. And so that's an example of a use of code confidentiality that is either easier or harder to do in various technologies, or various vendors, or various models, or various pieces of software middlewares that go on top of that. Authenticated launch is the ability to say, is the code that's running, is that only the code that I allow, or do I, or that would be a yes, or no would be, I allow any code to run, but it can't get access to the keys. And so some TE technologies can allow multiple enclaves or instances to run that are all isolated from each other, but any of them can run, they're just isolated. That would be an example of no, and that's why I say that it varies. Programmability, we tend to focus on things in TEEs that are programmable. Testability, I'll talk more about that in a little while. And then recoverability is if I've been compromised in some way, is there ability to get back into a good state in a way that you know that it's back in a good state, as opposed to I don't know if it's compromised, I just hope. Okay. So that's what their definition of the rows are. And the point is the different rows, other than the top three, may vary, and it's still called a TEE, and that's an opportunity for differentiation and innovation. Next slide, please. So that's the security comparison, but you might ask, well, how does things scale, right? Don't TEEs run slower and so on? So this slide compares, what if you're not using a TEE, you're just doing classic computation, versus what's the scalability if you start to use a hardware-based TEE, and how does that contrast with other techniques like, say, homomorphic encryption and so on? And so at a very high level, and again, things vary by technique and by vendor and by model, and it's an area of innovation and differentiation and so on. But at a high level, you can see that, of course, you're going to get the fastest, best, highest scalable performance without using a TEE. In other words, anytime that you start introducing security, you're going to get some degradation in performance that you're paying for in order to do the security operations. A hardware TEE, in the job of the vendors and models and open source projects, is to try to provide as high a scalability as possible, given that you're trying to keep those security guarantees. And by contrast to things like homomorphic encryption, because then you're having to do operations on encrypted data, you're limited to things that, as shown on the previous slide, are only circuits. And so typically today, the homomorphic encryption techniques are not as advanced in terms of the amount of scalability, other than the ability to scale out across machines. You can see that one is good, but the other ones tend to be more limited so far. And so we talked in the previous slide about when you combine technologies that you increase security. The corollary is that when you combine technologies and you say, I want to use multiple things in the slide together, you know, TEEs and homomorphic encryption together, then that generally lowers scalability because you're raising security. Okay. So there's a spectrum that you can choose the right point in the spectrum. Next slide, please. So now let's talk about the threat model, which is one of the most frequently asked questions that we get, right? What are you protecting? What are you protecting from boom? So here's the goal of what we're trying to do in confidential computing. Our goal is to reduce the ability for the owner or operator or pwner of a platform to access the data and code, and to reduce that ability sufficiently that the path is actually not economically or logically viable. Okay? In other words, we're trying to make certain types of attacks against data integrity, code integrity, and data confidentiality. We're trying to make them be not practical. Okay, that is our job. Next. And so there are things that fall in scope for the CCC threat model, and things that fall out of scope. So here's an example of things that are in scope. Okay, typical software attacks against the host. I'm going to attack the host operating system. I'm going to attack the BIOS or the firmware, whatever it is. I'm going to attack the protocols, whether they're attestation protocols or the protocols that the actual workload is running. Cryptographic attacks. I want to find a weakness in the algorithm or downgrade attacks, that kind of thing. Basic hardware attacks. If I have physical possession of the device for some period of time, you know, I've got access to it for an hour because it's the middle of the night or something like that, right? What type of attacks can I do? Can I inject things? Can I extract things? What can I do? And then basic upstream supply chain attacks, right? So I intercept a device in delivery and in between the factory and the customer's premises or the installation of it, then I can do certain things at that point. Next, the things that are examples of things that are out of scope would be much more sophisticated hardware attacks. And so if I steal the device and I'm a nation state and I start doing things like chip scraping or I apply an electron microscope, those things are typically considered out of scope for the threat model. All right, if I can disassemble the stuff at an atomic level, that's way beyond what we're looking at in the threat model. Similarly, things that are out of scope, not because they're not doable today, but because they're at a different point they're more like a social engineering attacks, right? So social engineering attacks are more out of scope. And so an example would be inside the factory, if I can get the wrong key injected into the device at manufacturing time, okay? Or if I can do a social engineering attack on the admin of the device after it's been installed. Things like that are considered out of scope for the confidential computing part of the threat model. Okay, next slide. Now, just like we mentioned that different TEs and different techniques have varying degrees of resistance to attacks in the matrix that I showed earlier, and even different degrees to which extent the optional properties are there or not there at all. But this is particularly true of differentiation in terms of robustness to integrity attacks, rollback, and replay. So an example would be, are they robust to physical tampering? To what extent are they robust to physical tampering? And so to address things like integrity attacks, rollback attacks, and replay attacks, this is where attestation comes in as an important way to detect and mitigate such types of attacks. Attestation is also a very complex topic. So let's say, what do we mean by attestation? And so one definition of attestation, which we kind of like, is to allow an entity, which we're going to call the verifier, which is another entity that wants to get some trust in things, to allow the verifier to gain some confidence in how trustworthy the attesting device is, or the attesting entity is, the attesting workload is. The attester is just the generic term that we use. How confident are they that the attester is themselves trustworthy by obtaining an authentic and accurate and timely report about the software, data, hardware state of the attester? So in layman's terms, that means that attestation just allows you to know what's running underneath your workload, right? What is your workload running on, and has it been loaded correctly? So for example, are you sure that there isn't some middleware layer that's been injected in between your workload and the underlying platform, even if there's a hardware TE? Do you know that there's nothing in between? And this is where things like attestation come in. That's super important, because that allows you to get a view of that complete stack of stuff between your workload all the way down to the hardware TE. So here's an example application, just going back to Nelly provided us a number of use cases. So let's say the use case is, I have an application that manages cryptographic keys, right? And I want to have that application be running in the cloud. And maybe that application releases keys to other entities that might be running the cloud, or even on the edge or in a user device. And so how can TEs help with that particular use case? So we talked about how the core capabilities are data and code integrity protection, data confidentiality. And so for those three things, like I can protect the keys itself, those are the core capabilities, right? That's part of your definition of a hardware TEE, that it won't leak those things or allow modification of those things. Okay. And we said, how do we know that it's the right workload? That say your key protection service isn't running on top of some middleware that might have been injected by an attacker. And so that's where things like attestation come in to verify that it's running in a way that you think it's running. And it really is running on that particular hardware TE with a particular version and firmware of the right security patches and so on. So attestation is what gives you the workload protection. And then finally, you have protocols that communicate with that to say, ask for a key or to ask for an operation on a key, consuming a key. And so that's where you need to protect, your transport protocol. And so the transport protocol implementations, as long as the transport protocol, the security part, whether it's TLS or something else, as long as TLS terminates inside the TEE, then you have that tie between protecting data in flight and protecting data in use. Because the termination is inside the TEE, it provides a connection between them. Next slide. So the last part of the threats that we often get asked about is, well, what about side channels, right? I keep hearing all the stuff about side channel attacks in the news or in articles or research papers and so on. Because this really is a relatively, as things go, novel attack chain against TEEs. And so there's been a significant area of research in the last couple of years. And a related problem is that if you look at hardware vendor literature, often side channel attacks are considered out of scope for that literature. And so there's this gap that says, well, what do I do? Where do I get the right information? How do I mitigate things? And that's where we in the CCC are trying to step in, because we are a collection of those hardware vendors and researchers and projects and so on. So the first response that we give is that although there's lots of things that have shown up in research papers, so far, we haven't seen things that are actually practical in the wild. So very limited utility in the wild, I should put it that way. And so today, we're not actually seeing them in practical use. Now, that doesn't mean that there couldn't be ones in the future. So they're certainly in scope for our discussions here. But so far, they're more research than they are in practice. And our goal is to stay ahead of the curve and to make sure the mitigations get out there before they actually become practical. Remember, our security threat model was to make the attack vectors against TEEs be impractical, okay? Not necessarily theoretically impossible, but impractical, so that it's not an attractive vector economically or financially. And so the industry is working to address the research ones that have been found, or the ones that have been found by research. Those mitigations and fixes have been done in software and microcode, and then they'll be rolled into subsequent hardware generations. But again, so far, we're not seeing them in practical use, and our goal is to stay ahead of that curve. Next slide. And so, okay. And so the point is that until, as the hardware vendors work on putting the mitigations into their next hardware generations, in the meantime, then it's the firmware, the software that provide those mitigations in the meantime. And so there's at least 4 ways that we've seen that mitigations can be done, and that we have projects working in, whether it's in the CCC or out of the CCC. So one is in the application itself, right? So I have some workload, and in order to mitigate the particular side channel attack themselves, I can change the software such that mitigation is applied directly by the application. We can also do things inside the compilers. There are some compilers that have inserted the mitigations such that if I pass, say, a flag to the compiler, then I get those mitigations compiled into the application. So I can do it at compile time or build time without having to change the application code. Third approach is if there's an SDK model. So the thing that the application is compiled, there's a library that links with, and the mitigations are inside that library. So maybe it's using, say, a crypto library, and then the mitigations can be put into that crypto library if the side channel attack is against the cryptography. And the last one is sometimes you have applications that run inside an environment at runtime. And so the mitigations can be done by the runtime environment without changing the application. And so we see techniques in all 4 of these areas to mitigate the side channel attacks that have been found by research so far. And then lastly, I would say all of these mitigations are within the scope of the CCC and in scope of discussion within the Technical Advisory Council that I chair. And so anybody that wants to work in these areas and any other organizations that work in these areas, we are certainly working with or would like to work with if there's other ones that are interested in this area that we don't already work with. So that would be great. Because our goal is to enable customers to have the confidence to use confidential computing, feeling confident that they can adopt things without having to worry about such attacks and things becoming practical. And so to talk more about adoption, I'm going to hand it over to Ava, who's an open source program manager and longtime open source advocate. So thank you, Ava.
Thanks so much for the intro, Dave, and thanks for all of that excellent discussion of security promises that trusted execution environments provide. To start talking about the adoption of confidential computing, I want to reiterate that all the innovation in this space is rooted in hardware evolution. Several member companies, as you saw on the slide earlier, are chip makers who are continuing to add capabilities to enable application memory to be protected against threats that could come from the host or other sources, as Dave just discussed. For end users to benefit from these capabilities, application developers need to have their tools enlightened. Whether through consuming a bare metal server or VM or containers from your cloud provider, or leveraging an integrated development platform on top of your preferred infrastructure provider, all of these hardware capabilities need to be exposed through higher level abstractions and consistent developer experience or production experience to be created for workload portability across TEEs or across cloud providers. So I'd like to talk for a moment about the work underway to achieve that and the open source projects currently in the consortium. Today, we have 2 projects that have officially joined and several more that have applied and been reviewed by the Technical Advisory Committee and approved. They're just going through the final paperwork right now. You can find this list up on our website. So with 8 projects in the consortium and under review by the TAC, we've observed a couple patterns and grouped projects into 2 paradigms based on how they enable the usage of a hardware trusted execution environment. Next slide, please. The first paradigm enables application development directly, whether you're writing an application, a new one, or you're making modifications to an existing one, by integrating awareness of the TEE directly into the application. It's memory management, it's logic flow, it's inside it, right? Then you can protect the data integrity and confidentiality within your application runtime. And to enable this, one might use any of these 3 SDKs, in the Open Enclave SDK, Intel's SGX SDK for Linux, or Keystone. While these are all C or C++ SDKs right now, we've seen interest for SDKs in other languages. None have yet been proposed to join the foundation, but I imagine folks might create those in the future. And the second, and at this point more popular paradigm, is to enable the deployment of an existing unmodified or mostly unmodified application into a trusted execution environment. Now I say mostly unmodified because these projects, some of them require the application to be linked against muscle instead of glibc, for example, which, while that isn't strictly a change to the application code, it might be a change to your deployment workflow or the base Docker image you built from. Or some of these projects might only support a specific set of tools or languages for their deployment. And so both of these paradigms, the application development or the application deployment paradigm, are discussed at much more length in the Outreach white paper, which you'll find a link to on our website and the end of our presentation today. So to enable all of this, and at the bottom of the layer, bottom of the stack, we have the TEE providers who are making actual changes in CPUs or other types of chips that must be exposed in some way up the stack, typically through a device driver, a hypervisor, something like that. And above that, we have this middle layer. At the very top of the stack, we have all the new applications that are being developed, whether it's an end user application, as Nelly discussed, or a new blockchain or a new ML service, which is itself a building block of new and more secure services for users and customers. In the middle of these two, we have a layer filled with innovation and emerging patterns. And this block diagram is not intended in any way to be proscriptive. It's not like you need one of each of these. This is merely a representation of the groupings that we're beginning to observe form as the space starts to mature. It's also not intended to be limiting in any way. All projects are welcome in the consortium as long as they align with the mission statement discussed earlier. And we'll probably end up realizing that there are more categories of software and open source that fits in this space as time goes on. So at least for now, this middle layer is where all of the open source projects in the consortium seem to fall, and where many of our member companies are rapidly building out new products and services. On this slide, I've just shown a couple of the projects. I haven't listed every member project, and a couple things I have listed, like OpenSSL, are not member projects, but still useful in this space and relevant. This slide, like the one before it, is only illustrative of categories we're seeing where innovation is taking place and provides a lightweight mental model for how you might think about the components you need to incorporate in your application development or your deployment pipeline. In other words, you might need some of these, but you probably don't need one of each of them. And each project provides protection in slightly different ways. Of particular note is that box on the right, AAA, which in this case stands for Authentication, Authorization, and Attestation, and Policy Management. At the moment, this appears to be a key component in enabling all the applications that we're observing folks build, but we don't yet have any open source projects that fill that space today. We do have a lot of our member companies are building out solutions there. And that being said, we also have a lot of initial discussions forming in the consortium, just beginning to take shape about how to create a consistent attestation model or consistent metadata definitions across TEE providers or across cloud providers. These discussions are all pretty early stage, so if you're interested in contributing, please come join the mailing list or in our weekly meetings. We'd love to have you. Thanks for having me. I'll hand it back to Seth.
Thank you, Ava. Before we get to the Q&A portion, I'd like to point out a few things. I think Ava and Dave referenced them, but if you would like to learn more through reading our more detailed white papers, you can go to confidentialcomputing.io/whitepapers. You'll find two different white papers there. One is done by the Outreach Committee, which is kind of an introduction to confidential computing with use cases that are common. We've kind of done a survey of the use cases and described them there. The other one is produced by the Technical Advisory Council and has a lot of the data that Dave presented around the threat model details, the definition, the characteristics. So I highly recommend that you take a look at both of those white papers if you're interested. We also have a capability to sign up to receive updates through confidentialcomputing.io/news. So if you want to be kept up to date, we use this sparingly and we'll only update with major things. So please sign up for that. We also encourage you to ask questions or continue the conversation through social media on Twitter, LinkedIn, or through our website. So with that, you have a Q&A button at the bottom of your Zoom interface. If you have questions, please type them in there and I will direct them to the panelists. So let's get started. I will pull up the questions here. Give me a second here. So let's start with Daniel asked, if I am not mistaken, we also need to trust the hardware vendor not to collaborate with the platform. So Dave Thaler, would you want to take the first shot at answering that question?
Sure. So Daniel, I'm not quite sure what you mean by platform, but I'm answering your question generically. One of the goals of confidential computing and security in general, right, is if you look at your trust model, which is what you're really asking about, we want to minimize the number of entities that you want to trust, okay? Because every entity that you have to trust is potentially an attack vector, even if it's for social engineering or some nation state attacker or whatever. And so it's how many different entities do you have to trust, okay? And so, yes, you have to, so the minimal answer that you could get to is you have to be able to trust your own admins, right? If you're the customer, right? Your own admin, the humans that are managing things, and whoever is the hardware vendor of the security chip that's providing your hardware-based DE environment, right? That's the minimal set, okay? Now, any of those minimal sets, you could choose to trust additional entities. You could trust, a tools provider or a cloud host provider or whatever it is, right? But that's your minimal set. If any of those entities, your own admins, the security chip vendor, themselves collaborate with, and by collaborate with, meaning if they were to release secrets or bring into what we would call the trusted computing base, then yes, you have to trust them too. And so if you want to get down to that minimal set, you not only have to trust just those two entities, your own admin humans and the security chip hardware manufacturer, but you also have to trust anybody that they themselves are bringing into the trusted computing base. And so I think the answer to your question is yes. I wasn't sure what you meant by platform, but that's a long answer, which is a little bit more generalizable than the way that you asked the question. So.
Okay, thanks, Dave. One of the questions that is relevant to what Nellie was talking about was, can you talk more about the most mature use cases where CCC or confidential computing is being used? And let me start off and just, I'll give my own opinion, and then we'll let Nellie have a chance to answer that as well. We've seen the first one that Nellie talked about. There's quite a few people who use it in the context of key management, secrets protection, protection of tokens. That's a very common, very mature use case. The other one that seems to be very popular from my interaction with customers is whether you call it privacy preserving analytics or multi-party computation or multi-party analytics. It's the idea of combining data from multiple parties without exposing to do analysis, AI, ML, without exposing the underlying data or algorithms to one of the other parties. So those are two of them that I've seen be kind of more common and mature, but I'm sure there are others depending on which types of customers you interact with. So Nellie, do you have, what would you consider the most common or mature use cases in confidential computing?
So says you outline probably a few that very mature and very well understood, but what we've seen rolling confidential computing in the cloud, there are very many use cases that again prior probably would not be possible to accomplish. And it, depending on the vertical or sector that working on those use cases. So for example, for financial sector, we see, as I mentioned, making the payment from personal devices and also processing payments. There's very many customers trying to deal with investment and wealth management, lending, trading, personal banking. It's all of those use cases are very well understood by financial sector and fintech, and moving them to confidential computing becoming very kind of obvious next step for them. There's a lot of algo processing, trading that happening in real world and happening based on very sensitive data and sensitive algorithms that customers and again researchers want to protect. For healthcare, no surprises with rise of global pandemic that you very well aware. There is plenty of work done to process very sensitive data in the cloud in particular, because the scale is mandatory to do, again, patient data prediction algorithms, etc. So patient management and protecting their sensitive data is becoming very, very common use case that we see more and more often. And as you move to the, again, even basic media, gaming, ads management, all of those different verticals have access and process a lot of personal data, and protecting their users and protecting their clients becoming very, very paramount for them. So we see variety, really variety of those use cases. And because we're trying to ensure, as you all said, that customers don't have to change too much, they can use their simulation models, their analytics without too much modification of what they do in the workloads. It's becoming a very mature case to run in very scalable cloud environments. It's what we see very often. On personal devices, no surprises, the same effort is happening, because trusted environments, or TE, as Dave mentioned, are well known on mobile devices from all vendors. And there are a lot of efforts to get more and more processing done on those trusted execution environment when it's coming to sharing secrets, processing passwords, dealing with sensitive information of the users as well on the devices themselves.
Thank you, Nellie. I think the other thing I would add is that while there are these very specific use cases that Nellie talked about, it's applicable to any application, particularly in public cloud. And there's been a lot of progress this past year in terms of the amount of cloud infrastructure available that enables confidential computing. So, a year and a half ago, there were very few cloud providers that offered infrastructure that was enabled for confidential computing, and there's been a major shift and increase in the available infrastructure. So really the way I'd look at it is any application that would benefit from protecting the sensitive data in the application is a potential confidential computing application.
Absolutely.
Now those, the question was, what are the most mature? So those are kind of like the early adopter kind of use cases, right? But we expect that it'll get much broader as the infrastructure becomes more pervasive, the open source capabilities increase, and the vendor ecosystem builds out more kind of commercial systems around confidential computing. Next question, let me direct this to Dave. There was a comment that I disagree that homomorphic encryption provides data integrity. It's malleable by design. Dave, do you want to comment on or respond to that since you touched on that in your section?
Sure. So the question itself mentions just homomorphic encryption, but I wanted to use this as an opportunity to reinforce the relationship to confidential computing. And so since it's anonymous, I don't know who questioned this, but the point that the questioner is making, I think, is very similar to the point that I made about TPMs, right? Where if you ask a TPM to encrypt something, it will encrypt whatever you give it, right? It doesn't verify that that's the correct data. It just says, okay, I'll encrypt that, and you keep the key secret, right? And I believe that the questioner is saying, well, doesn't that apply to homomorphic encryption too, right? I can feed in something, anyone can encrypt some value and add it to the original data. The point that the slide was talking about when I said it provides data integrity is the encryption is provided at the edge in homomorphic encryption. And so in a typical example of homomorphic encryption, let's say that the homomorphic encryption algorithm is running in the cloud and the encryptor is running on the edge. That's not the only case, but let me use that as an example, okay? So the cloud location only sees encrypted data, and the data integrity is provided by that encryption, right? If you were to change some particular value in there, the encryption wouldn't hold anymore. And that's how it's different from, say, a TPM. However, the point is still true that you can encrypt anything you want on the edge. I mean, the questioner's point is still true that you can encrypt anything that you want on the edge, and homomorphic encryption, well, just deal with it. And so in that sense, it's a little bit analogous to the TPM point. And this is where I was saying, there's a use case when you're using homomorphic encryption. Even if you're using homomorphic encryption, there's still a value proposition for using confidential computing, right? So where is it that you're doing the encryption, right? When you say anyone can encrypt some value, where is that encryption happening, okay? Our position is that encryption should be happening inside of a trusted execution environment in order to provide that full level of data integrity that the questioner is asking about. And so again, this is a use case for confidential computing, even if you're already using homomorphic encryption. So that's the answer.
Okay, thank you, Dave. Let's get Ava involved in this discussion. We have a question around what is the relationship between the CCC and OpenSSF? Maybe you can take the opportunity, if there are any other organizations that are related, to also talk about the relationship and how we interact and coordinate with other groups that are in related categories.
Sure. So I'll start with describing the OpenSSF. It's the open source software, open source security foundation. They're focused on securing open source software, build and supply chain, tooling, monitoring capabilities. They're not, that foundation is not focused currently on hardware security. We don't have at the moment a formal relationship with them, but some members, myself included, also do collaborate with them. And that, I think, at a high level describes our relationship with a lot of other foundations as well, that we have members in the CCC who are also members or involved in other open source foundations. For example, myself, I'm also involved in the CNCF, the Cloud Native Computing Foundation. And so there is a little bit of work starting up between the CCC and the CNCF relating to, how do cloud native projects use the capabilities of confidential computing to improve the security of containers. And so I anticipate that we will see discussions like that increasing over over time. I could imagine the OpenSSF starting to do things like using attested builds and leveraging projects from this foundation in their projects, but we haven't started that work yet.
Dave, I know you're involved with like IEEE and some other standards bodies. Do you want to touch on how CCC both interacts and relates to those standards bodies?
Sure. The one that I participate in the most is the Internet Engineering Task Force, IETF, which I can see that there's several of the attendees on the call are names that I recognize from that organization. And so for that one in particular, and the same would apply to other organizations like the Trusted Computing Group, FIDO, and so on, that would be in the overall space, is that the CCC focuses on the open source projects, and those are the ones that Ava walked us through a number of those. Whereas the other organizations tend to focus on the specifications, and so it's a complementary way of working together, division of labor, where often it's a lot of the same people, if not the same organizations, working in multiple of these organizations together. And so the CCC wants to work closely together with any standard specification organization that does standards in the space for protocols or for hardware or whatever, such that the projects that come into the CCC, we provide a home for, and that's why we want to keep the terminology unified and be able to cross-reference specs. And so you can see, if you were to look in the TAC white paper, you'll see cross-references to specifications from these other organizations. And we would invite the other organizations to reference our white paper too for further discussion around confidential computing. But yes, there's a number of different organizations that are involved, some of them that we're already working with. Again, IETF is the one that we're working with probably the most closely. But on things like attestation, there's many organizations involved, where the IETF has been hosting some of those discussions, where the CCC and many other organizations are cooperating in those discussions between TCG, FIDO, IETF, CCC, and so on, for the different areas of different areas of the landscape in the industry. I will also say that there are some relationships or potential relationships with government organizations as you start having regulatory requirements and so on for certain levels of security or compliance things. All of these are organizations, compliance labs are things that are opportunities for collaboration that we are eager to continue and have more collaboration with. For example, a couple weeks ago, the NIST organization in the US had a webinar on securing IoT, and I was one of the invited panelists there. And I got in a plug for the Confidential Computing Consortium in the middle of the webinar there. And so having great cross collaboration between organizations and stuff that helps all of us.
I'd like to add on to that real quick. There's a follow-on question about, is there any effort to do attestation with these hardware vendors in open source? And I would say we've had a couple little discussions in the CCC, but and there is the Open Enclave SDK project. And if folks want to get involved in writing open source projects to do that in the consortium, we would absolutely welcome your contributions. Please do join us. That is an area we're definitely interested in.
Okay, I think we're going to have to cut off the question. There's a couple categories of questions that I just wanted to address by category. We're not going to answer questions about individual vendors' solutions, and there were a few related to one of our member chip manufacturers. So if you would like, we're happy to pass along those questions to the individual vendors and get them answered. However, if you were an anonymous attendee and asked that question, we have no way of getting in contact with you. So I suggest that you reach out through our website or email one of the presenters your question separately, and we're happy to direct that to the specific vendor. Also, there were some questions around like, hey, if I'm interested in doing this, like, how do I find out, what solution would be best for me to do a TEE, or what cloud providers offer services? We're not going to get into the specific vendors on this, but I do suggest you go to our website. We have all of our members listed on the website. There are many, I'd say, most, if not all of them, have an existing confidential computing enabled infrastructure that span different cloud providers and geographies and approaches. And then also we have open source projects listed on the website that you can learn more about, and we can help direct you, through the website. So thank you, everybody. We're at time now, so we're going to conclude the webinar. And again, you will receive a recording of this, and we encourage you to sign up on our website to get notifications about future webinars. Thank you. Thank you, panel.